Intuitionistic mathematics, founded by L.E.J. Brouwer, is a branch of mathematical philosophy that focuses on constructive reasoning. Unlike classical mathematics, which accepts the law of the excluded middle and non-constructive proofs, for example, proofs by contradiction that establish the existence of an object without constructing it, Intuitionistic mathematics insists that mathematical statements are only meaningful if they can be explicitly constructed. What is accepted as given in intuitionistic proofs? 1. Axioms and definitions. Intuitionistic proofs rely on constructive axioms and definitions. For example, sets are defined explicitly in terms of their elements or constructive rules for membership. 2. Logical rules. Intuitionistic logic differs from classical logic in its rejection of the law of the excluded middle, which states that a proposition is either true or not true. In intuitionistic mathematics, a proposition must be constructively proven true, or its negation must be constructively proven true. Double negation elimination, which in classical logic allows one to infer that a proposition is true if it is not false. In intuitionistic logic, this is not allowed unless the proposition itself can be constructively established. 3. Acceptance of proofs. A proof must provide an explicit construction or algorithm. Merely showing that the negation of a statement leads to a contradiction is insufficient. Examples of intuitionistic theorems, with constructive proofs. Example 1. Intermediate Value Theorem, constructive version. Statement: if a function is continuous on a closed interval from a to b, and its value at a is less than 0 while its value at b is greater than 0, then there exists a point c in the interval such that the function value at c is 0. Constructive proof outline. 1. Use the continuity of the function to explicitly construct a sequence of approximations to the point C by bisection. 2. At each step, choose the midpoint of the current interval and evaluate the function at that point. 3. Refine the interval based on the sign of the function at the midpoint, ensuring that one endpoint of the interval remains less than 0 and the other endpoint remains greater than 0. 4. The process converges to a point C where the function value is 0. Example 2. Fundamental Theorem of Algebra, constructive version. Statement: every non-constant polynomial with complex coefficients has a root. Constructive proof outline. 1. Approximate the polynomial over a sufficiently large bounded domain in the complex plane. 2. Use constructive minimization techniques to locate a point where the magnitude of the polynomial is close to 0. 3. Show convergence to a specific value of the variable such that the polynomial equals 0 through successive approximations. Example 3. Brouwer Fixed-Point Theorem, constructive version in low dimensions. Statement: any continuous function from the closed interval from 0 to 1 to itself has a fixed point. Constructive proof outline. 1. Discretize the interval and locate approximate fixed points by checking when the difference between the function value and the input is sufficiently small. 2. Refine the grid iteratively to construct a sequence converging to a fixed point. Examples of theorems not accepted as true in intuitionistic mathematics. 1. Law of excluded middle, L.E.J. Example: For every real number x, either x equals 0, or x does not equal 0. Rejection reason: without a constructive proof of whether x equals 0 or x does not equal 0, this cannot be universally accepted. 2. Non-constructive existence theorems. Example: there exists an irrational number x such that raising x to the power of itself results in a rational number. Classical proof: assume x equals the square root of 2. If raising the square root of 2 to the power of itself is rational, we are done. If it is not rational, then consider the number raised to its power. Either case works by the law of excluded middle. Rejection reason: this relies on a non-constructive disjunction and does not explicitly construct such an x. 3. Double negation elimination. Example: if it is not true that a proposition is not true, then the proposition itself is true. Rejection reason: constructively, proving that a proposition is not false only shows that it cannot be disproven, not that it is true. 4. Bolzano-Weierstrass theorem, unbounded case. Classical version: every bounded sequence in Euclidean space has a convergent subsequence. Constructive challenges: explicitly constructing the convergent subsequence for arbitrary sequences may be impossible without additional structure. Intuitionistic mathematics emphasizes constructive reasoning and explicit methods. Many classical theorems are reformulated to accommodate these principles, and some are outright rejected due to their reliance on non-constructive reasoning. This approach aligns closely with computational methods, as every proof corresponds to an algorithm or explicit construction.